Assalamualaikum warahmatullahi wabarakatuh. This is Statics chapter 5. We will begin a new chapter, and we have already covered chapter 1 until chapter 4, which is all our foundation for this chapter and another chapter onwards, right? So chapter 5 deals with equilibrium of a rigid body, and of course we will be learning some things related to solving equilibrium of a rigid body, including free body diagram, and also support reaction, right? So yeah, we will begin 5.1 and 5.2, equilibrium of a rigid body. Now, to refresh, we have covered 4 chapters before, and all of this will be a foundation for this chapter. And because in chapter 3 we actually have covered equilibrium of a particle, right? So basically, if you have a particle and you have forces acting on it, so as you can see, every force will be acting on the same point, right? Hence, there's only force reaction and there's no rotation moment, right? And in chapter 4, we have covered how to understand what happened. For example, if you have a force here, it not only have the push downward effect, but it also have the tendency for this type of rotation, right? Rotation clockwise or counterclockwise depending on the force and the location of the force, right? So when we deal with equilibrium of rigid body, this is an example of rigid body. It is rigid. So if you have a force here, here, etc., so the distance between all the forces does have an effect in terms of the tendency for rotation. Hence, whatever we have covered in chapter 4 will be something important in chapter 5, and what we have covered in chapter 2 also will be important, because normally we have to know, especially in a 3D body, we have to know how to deal with getting every forces into Cartesian vector form, because that's how it is easier to calculate the moment, etc. Right? Having said that, let's go straight into this chapter. You can refer to the slides. This particular recording is for 5.1 and 5.2. Right? So in the slide, they goes into some application examples to show that there are various problems in the real engineering world where it require you to understand this chapter, how to actually represent the problem into an idealized model, and then free body diagram, and then calculation using equation of equilibrium, right? So we'll just go through that. Now, hopefully you have understood chapter 3 where, and also I think you have learned this before anyway. When we say the body is in equilibrium, so there's 2 conditions that have to be met. One is, so when you say equilibrium, right? So there's 2 conditions. One is summation of all forces should be equal to 0, right? And also summation of all moment should be equal to 0. Let me check. I think that is in the frame, right? So this is in terms of Cartesian vector notation, right? In terms of scalar, basically summation of f is basically you have the 3 components: summation of fx equal to 0, summation of fy equal to 0, and summation of fz equal to 0. This is if you are talking about 3-dimensional, right? And in terms of moment, you have summation of mx equal to 0, summation of my equal to 0, and summation of mz also equal to 0, right? So when everything equal to 0 there, then that is where equilibrium is achieved, right? So when the question says this is in equilibrium, then all of this must be achieved, right? Okay, so that's the understanding, right? And then in terms of we go to the next slide, in terms of the process of solving rigid body equilibrium problems. So the slide actually shows from the actual original structure or problems or the bodies itself, and how it is transformed into the idealized model, right? And then from the idealized model, you have to know how to convert it into a free body diagram, right? In terms of the exam, normally you will be given the idealized model, and then you have to convert that into free body diagram. Of course, in the real world, when you are working as an engineer, there's no one there to to actually give you the idealized model. You are the one who, from looking at the actual problem, you have to be able to simplify it into an idealized model and then convert it into free body diagram, right? So because in the real engineering world, no one will give you the problem in terms of the exam diagram, right? You have to look at the real thing, whatever these things, and then convert it yourself, right? However, because we are learning this for the sake of an exam, not that we are learning for the sake of an exam, but we are learning how to solve exam problem, right? So hence, we straight away go into the idealized model and how to get that into the free body diagram, right? So basically, free body diagram should show all the external forces acting on the body, right? And then you can apply the equation of equilibrium. Now, hopefully you still remember from chapter 3 what is a free body diagram, right? So, in terms of the free body diagram itself, before we go to the step by step, right? Free body diagram. Free body diagram. Right? Hopefully the focus of the camera is okay. Right? Free body diagram. It's outside. Okay, now inside that. First of all, it should be a diagram. Right? That's obvious. And then it is a diagram of a specific body, right? So this is where we have to decide what is the body of the free body diagram, right? Meaning if we have a problem, we can actually select this part is the body, and hence all external forces acting on the body, it should be in the free body diagram, right? And it also have to be free, right? What this means is that the body itself should be free from the surrounding, right? So I don't know what to say. Now, if we have, let's say this thing here, right, sitting on something like this, right? So if I say this is my body, right, that we consider, the body that we consider. So the drawing should have only this, without whatever support, table or floor or ground or whatever, right? So if you still draw like this, with this inside the drawing, that is not a free body diagram, because this body is not free from the surrounding. This is the surrounding, right? So it is only having this one, and the support here is replaced by the force that is supporting this body, right? Now, when I mention the body can be whatever you want, depend on what you want to solve, right? If, let's say, what I want to solve is this thing over here, right? Without this, so the body have to be drawn with only this, right? I'm not sure if this is a good example. Right. For example, this is a water bottle, right? Now, again, if I consider this as my body, the whole thing, then when I draw it, this one is the body, and then you have the support reaction from the ground, and then maybe its own weight, etc., right? But if I say, no, I want to consider what is this reaction between these two, and I consider this is my body, the body that I draw, so the drawing should have only this, right? And then whatever reaction here, of course, in this chapter we do not yet learn the reaction between these two, right? But this is just an example. If I say this is my body and this one is external, so it shouldn't be having like that, right? So this is just an example of how to understand when we say free body diagram, it should be free from the surrounding. So if I am the examiner, if you still draw the external thing outside of the body in your so-called free body diagram, you will lose mark there, because that is not a free body diagram actually, right? So yeah, make sure you understand that. In terms of the step, so as you can see in terms of the slide, they say first step is to draw the outline of the body, right? So the outline shape, right? So the water bottle, the cup, etc. So just draw the outline, right? So that will be the body, and then it must be free from the surrounding, obviously, right? So in chapter 3, right, for example, if we have like a ring there, and then we have a cable going there, cable going there, cable going there. So when you draw the free body diagram of the point, it should be free from all the cable, right? You just replace the cable with the force, right? If you still draw the cable, if you still draw the point somewhere else, that makes it not a free body diagram because it's not free from those things, right? Similarly here, if this is the object that becomes the body, so it should be free from any strings, any support, etc., right? So draw outline, it should be free from the surrounding. Second, you have to show all the external force. Right? When we say, and also moment, right? When we say force and moment. Because for now we already have learned about moment, and when we saw rigid body, it is possible to have moment, right? When you have a particle, it doesn't have moment because it is not rotating like that. But anyway, so when we say external, of course, because, for example, this is my body, right? It is sitting on a table, for example, right? So when I draw the free body diagram, it should be this only, right? Now, when we say external, meaning that this reacting to the table, so the table is the external thing, and it exerts a certain force there to prevent it from going down, right? For example, right? And we do not need to draw all the internal force. For example, inside here, there's a lot of things that have internal force against each other, right? Meaning that this marker here is reacting to this marker to the whole case itself, right? But that's all is internal, right? So when we draw free body diagram, whatever if this is the whole body that I'm considering, so I do not need to care about what happened inside. Internal force, no need. External force, meaning the body and what is external, right? If I'm considering this as my body, right? And it is actually reacting to whatever marker inside here, right? Whatever else inside, right? So when I draw this one, so everything outside of this one is the external. So this one reacting to whatever else inside, that is an external force, right? So external means external to the body that you decide to draw, right? So what you want to draw normally is depend on what is the question, right? So normally if this question is what happened between this and the table, then just take this whole thing as the body. If the question say what happened between whatever else inside, for example, what happened between this and this inside, right? So you will draw this as your body, for example, right? And hopefully you understand the idea. So that's just to clarify what it means by external, right? Because the other side of external is internal, right? Okay. And then label all loads and dimension on the free body diagram. So label, right? All loads or forces and also dimensions. Right? So it is not enough if you just draw an arrow, right? For example, if you draw the body, draw the arrow, but you do not label it, right? F something, etc., right? So meaning that is not a complete free body diagram. Your free body diagram is not complete without those labels, right? So it does say that all the known forces, all the known dimensions, etc., you have to note it. 5 meter, 10 Newton, 10 kilonewton, 10 Newton meter, etc., right? So you have to put the value if it is known. And if it's unknown, right? For example, we do not know the value of the force, and that is actually the force that we want to calculate. So you have to put label on it: FA, FB, MA, etc., right? X, Y for the dimension, etc. So all of this is a requirement for the free body diagram. To have an idea is whatever you will do or use in terms of the equation of equilibrium, right? For example, in the equation of equilibrium, you will have the forces, so either the number or the label FA, right, etc. So it should exist in the free body diagram. You cannot have something not in the free body diagram and suddenly appear in your equation of equilibrium. That is not correct, right? Something is wrong there. And also you have the angle, right? Theta or 15 degrees, 20 degrees, because when you calculate summation of fx, for example, or summation of fy, you will do that, f cos theta, etc. Right? So that theta must be in the free body diagram. You cannot suddenly have theta, beta, alpha, whatever, but in the free body diagram that does not exist, right? So it should tally, right? And you have to have the dimension, because when you do summation of moment, you have the force and the distance, etc. So the distance should be in the free body diagram also, etc. And the moments, etc. Right? So make sure you understand that. Right? Do not be surprised if you lose a lot of mark in your free body diagram in your exam if you do not fulfill all this. Right? So for example, you just draw the arrow, but you do not label it. So do not be surprised you lose a lot of mark there, because it's not a complete free body diagram. Alright. Now, the next slide goes into the support reaction, right? Because when we draw free body diagram and we just select this is my body, it does react to the surrounding, and we take out the surrounding, we have to replace by the forces or the moments or whatever from the surrounding, right? So we have to understand how to draw the support reaction, right? So in this slide, it just gives several examples of support that you can find in real world that is represented by the idealized model in the drawing. And right now we'll go into that one to understand how to draw, or how to first understand what type of moment, forces, etc. that exist, and then how to draw it. Alright. The idea is simple actually, right? So if, I'll just read first from the slide. As a general rule, if a support prevents translation of a body in a given direction, then a force is developed on the body in the opposite direction. Do you understand that? Hopefully you understand. But if you don't, basically what it means that, for example, again, this is the example that I'm going to use, right? It is on a table, for example, right? Right. So if a support prevents a translation of a body in a given direction, in this case, does this support prevent any movement of this thing? So basically, it prevents it from going down, right? Right now, we assume there's no friction yet, because later on in chapter 8, there might be friction, right? It also friction in this movement, but currently we assume my skin is smooth and there's no friction, right? Now, so the prevention is it prevents it from falling down, right? That's why it stays there. Without it just falls down, right? So meaning that it says if the support prevents a certain movement, then you have the force in the opposite direction, right? So in this case, the movement that it prevents is going down, right? Without the support, it goes down. But in this case, it prevents it from going down, meaning it provides the force going up, right? So that's why it doesn't go down, because the table provides this force going up so that it stays in equilibrium there, right? So that's the idea. If you have, what else? I don't know. If this one is also on the table and also it's have a wall there, right? For example, and it also prevents this from going inside the wall, right? It is not going there, right? So basically, when you draw the free body diagram, there's a force there that prevents it from going there, right? So that's the idea. Similarly, in terms of rotation, in terms of moment, right? So for example, if I have a support like this, right? So this support actually, for example, it prevents this from going up and down, right? This can go up and down. This one prevents it from going up and down. So it means that when I take away this one to draw the free body diagram, you have a force, for example, that way or that way, that prevent it from going up and down, right? Now, we will discuss more on then, because previously this one only prevent from going down. The table does not prevent it from going up, right? But this one prevent it both ways. It cannot go both up and down, right? So we will discuss on what is the implication in terms of the free body diagram. However, I want to just focus on the rotation, right? This also prevent this rotation, right? If something like this, it can rotate, right? But if you hold it like this, it cannot rotate either way, right? Hence, when you take out this one to draw the free body diagram, you have to draw the moment, right, that prevents the rotation. You understand? So that's the idea. That's the general idea. If it prevents the movement or motion, then you have the force opposing that direction. If you have a restriction, right, if you prevent it from rotation, then you actually have the moment that is actually preventing the rotation, right? So that's the idea. If it is free to rotate, then you do not have the restriction of moment. If it is free to move, you do not have the restriction of force, right? Okay, so let's go one by one, right? So there's a different type of support, so I'll just erase this one. So right now we are dealing with support reaction. Alright, so we are talking about support reaction right now. So let's imagine if you have like a roller, right? I'm just going first with the example in the slide, right? So if you have a roller, something like this, right? You have a roller. Right? And basically this actually have a roller and a pin. Right? When we say about pin, it means that, for example, you have a hole. If you have a hole and then you have the pin hinge there, so it is free to rotate, right? So in this case, if you understand what's going on, when you draw the free body diagram, right, you just focus on this one, you take away the whole thing. So the question that basically you are asking yourself is, does it allow or does it prevent this movement to the right or to the left, right? So when you have a roller, it is free to move, right? It is free to move to the right and to the left. Hence, you do not have any restriction. You do not restrict this movement. Hence, you do not have support reaction, right? So hopefully you understand. Support reaction is actually the force or the moment that prevent some movement or prevent some rotation, right? So there's no restriction there. However, is there any restriction going up and down? Is there? So this ground here is preventing it from going down, right? It doesn't prevent from going up. If you lift it, okay. But if you push it down, that ground will prevent from movement of downwards. Hence, you have a force upwards, right? You will have the force upward that prevent it from going down, right? So that's the idea. This one, because it's a pin, right? Does it prevent any rotation? No, right? Because a pin there. So if you have a hole and then you have a pin, it allows it's allow rotation, right? So the only restriction is going down. Hence, you have to draw like this. Now, if you draw like this, right? The arrow going down, this will be wrong. Why? Because the ground will never ever pull that thing down. It doesn't make sense. Understand? So hence, it cannot go down. The force can only go up, preventing it from going down. So that's how we draw it, right? So if you have the roller on a slope, right? For example, so the restriction is perpendicular to the surface in that way, right? So it prevents from going down. So when you draw the free body diagram, the force is there, which is perpendicular to the surface, right? So the idea is the same as this one. It's just that the surface is at a tilted angle. Hence, the prevention is that way, right? So that's a roller, right? So hopefully you understand. Of course, the same concept apply if you deal with rocker, right? Hopefully you know what's a rocker, right? It's those dude with long hair and the guitar. No, I'm not talking about the rocker. I'm talking about if you have a ground like this, something like that, right? Meaning that, I'm not sure if you are familiar with a rocking chair, right? Where you rock back and forth, right? So basically the idea is, this mechanism, it doesn't prevent movement in this way, horizontally, it doesn't prevent, but it prevents movement going down, right? And also it doesn't prevent on any rotation, right? So when you draw the free body diagram, it's just strictly upwards, which is perpendicular to the ground, right? So when you have a roller or rocker or anything of that sort, the direction is like that, right? So that's the basic, the most basic, where you have only one direction. Okay, let's have a pin. Pin support, right? So pin support normally is drawn something like this, right? So if you have the ground and then you have something like that, so this is a pin support, right? So when, for example, the mechanism is basically you have something and then you have a hole and then you have the pin there, right? So it's like hinge there that you can rotate, right? But you cannot move in this way because it's there. It cannot move this way because it's there, right? It's locked there, right? So in that case, how do you draw it? The free body diagram of this part, right? So basically it will be something like, hopefully you can guess this already. You'll have, let's say something like that, right? Because it restricts this movement, so you have a restriction there. It restricts this movement, you have the restriction there, right? It does not restrict the rotation. It's free to rotate, so you do not have any support reaction moment, right? Now the question is, why do I draw like this? Why is it not to the left? Why do I draw like this, not downwards? Actually, this is assumption, because it depends on what happened with the object, right? If the object is tend to move in this way, then the pin actually preventing it from moving that way, actually the reaction is that way. If the object tend to go that way, that the same pin actually have the force this way, right? But before we solve it, we might not know which is the direction. So we have to just to assume. So I can assume that way. I can also assume in the opposite way or in the opposite way, right? Or any other combination, right? So we assume, and when we calculate, in the end, if it's positive, then our assumption is correct in the direction. If it got the negative value, then the assumption is wrong, right? So you just assume and just let the calculation go, and from there you know the direction is correct or not, right? So not a problem, right? So that's a pin support, right? If it's something like this, right? So it's still the same, right? So basically the idea is you have a restriction in both axes, right? X and Y. Even if you have something like this, right? So when you draw it, you can still have X and Y, right? So basically, obviously, okay, some actually ask, why is it X and Y? Why is it not 1, right? Like when we have the roller just now, if it's at a certain angle, then we have the force in that direction, right? But when you have a pin like this, why is it 2, right? Why is it not just 1 force? Actually, if you calculate the resultant of these 2, you just get 1 force resultant, right? But the difference is, when you draw like that, you know for sure the direction of the force is that way. In this case, it depends what is the value of x and y, because it can go in this direction, etc., depending on the x and y component, right? So that is the meaning actually, right? So we do not know the angle because it is a pin. It just reacts to whatever forces elsewhere, right? And the support reaction can have any other direction depending on what happened here, right? So we'll have to just draw the x component and y component, and we will find the actual resultant later, right? So that's the idea. Alright, so that's pin. What about if you have a fixed support? Right? Fixed support meaning that if something like is cemented, right? If you have a wall and this is basically just cemented there and it's just fixed there. If you have some super glue, for example, you just fix here, right? So that is a fixed support. Now, so if you have something like that, for example, this is fixed there, right? So if you draw the free body diagram, obviously you have to take out the wall, right? That's the external, because this is the beam, the wall is external, so you have to take out, right? This is not a free body diagram, this is not a complete free body diagram, but when you say it's free from the surrounding. So the question is, does this wall allow the movement in this way? It does not, right? It is restrict. You cannot move, right? So you have one horizontal reaction force. Does this wall allow or prevent the movement up and down? It prevents, right? It does not allow. Hence, you have a force that way, right? The support reaction vertical, because it doesn't allow that movement. Does this allow for rotation, or it does not allow? It does not, right? You cannot rotate. Hence, you have a support moment there, right? Because that is the support moment that prevents the rotation, right? So when you have a fixed support, then you have, for example, if let's say this is point A, so you have EX, EY, and MA, for example, right? So you have the three support reactions there. And in 2D, that's the maximum basically, right? Because you only have this movement, and a rotation, right? So a fixed support, it doesn't allow for anything. You cannot move, you cannot rotate. So you have AX, AY, and moment, right? So there are a lot of other support type that you can just imagine. The question is just that, can it move? Can it move? Can it rotate? Right? So based on that, you should know what support reaction is there. Do you have the force in x-axis? Do you have a force in y-axis? Or do you have a moment? Right. So let's go through some example. Now, in example number 1, it's just basically just to see whether you understand, right? So basically, okay, I'll just draw it quickly. So basically, you have something like this, right? And then you have a pin support here. How is it? Something like this. There's a pin support, and then you have a link here, and then you have a spring here, right? So how to draw the free body diagram of this here, and also it does have a force here. So again, when you draw the free body diagram, the first is to draw the outline shape of the body, right? So in this case, it's something just like that. That's the outline shape, right? And then you draw all the dimensions and all the forces, right? So I'm just focusing on the force right now. So here you actually have the force F. Now here what do you have? This is a pin support, right? So it prevents from vertical and horizontal movement, but it allows for rotation about that pin, right? So basically you'll have X and Y component of reaction, support reaction here, right? Again, the direction is assumed. I assume upwards, I assume to the right. If I get negative, meaning it's the opposite direction, right? And then you have a spring here, for example, force from the spring. Of course, the direction depends on the condition of the spring. If the spring is being compressed, it wants to push back, so the force will be that way. If it's being stretched, then it wants to go back, so the force is going to be that way, right? And then you have the force here. Now, for this one, we haven't learned yet why it gives you this force, right? Because this is another pin, right? So again, we have learned when you have a pin, you have X and Y forces. But for something like this, then you only have that one component, right? We will be learning on that later when we reach on that component, right? Example number 2. Right. So in example number 2, actually it is quite interesting because it gives you the actual diagram of the actual thing in the real world, in the real world, or in the real life. And then you have to go to the idealized model before you actually go to the free body diagram, right? But for this one, I'll just explain from the idealized model to the free body diagram, right? For the actual real world to the idealized model, please take a look for yourself, right? Okay, so basically you have the platform, something like this, right? So if you notice that it's something like there's a pin there, if I'm not mistaken, yeah, and then there's a cable here, and also there's a weight, its own weight, right? So that's basically the idea of what is happening to this one, right? It is supported by this cable and supported by this pin. So if you want to draw the free body diagram, and you need to if you want to solve, then first is to draw the outline shape, right? So something like that. And then you have to put all the dimensions, so you have to, and then again I'm focusing just on the forces, so I'm not drawing the dimension, but in actual free body diagram you have to have the dimension. Alright, so pin, again it prevents from this movement, it prevents from this movement, but it allows for rotation, right? So what you have is just, in this case, what is the point? So you have AX and AY, because this is point A. Right, that's how you label it. AX, AY, BX, BY, because that's the point, and then X component, Y component. Right. And then it have its own weight, and also it will have that tension in the cable, right? So hopefully by now you have understand cable already, right? Because we have dealt with cable in chapter 3, right? Sorry. And cable can only be in tension, right? Because you cannot push anything with cable, right? You can only pull, right? So in this perspective, of course, the cable, the force from the cable is in that direction because it's pulling this upwards that way, right? So that will be just basically the forces in the free body diagram. Now, if you see the concept quiz in the slide, basically, okay, we'll just go through this one. Let's say there's a mesh there, and then you have something that goes through the pulley there, right? Right. So this is a pulley. How to draw the free body diagram? Right. So basically, first you have to identify what is the body that you want to draw. So I will just use this beam. Right. That beam is the body. Right. And I have to draw all the forces acting on the beam. Right. So obviously, this weight here have that force from the weight. Right. And at the pin here, you will have X component, Y component, because it's a pin, right? So what about this one? So actually you have this force and this force, right? However, you should already by now understand what is the effect of a pulley. When you have a pulley, this is the same cable going around the pulley, so the tension in the cable throughout should be the same. Hence, this and this should be the same tension, right? So, and then this is for example AX, AY, right? So that's how you draw free body diagram exactly. Right, so concept quiz, right? Okay, this is a task for you, right? There's a concept quiz there where you have like the beam, right? The beam that have a certain curve there, and then the roller at the end, and then they have the forces, right? And the question says, what will happen if you reverse the force or moment, etc., right? So please try this to see whether you understand or not, and remind me to ask in the class, right? So because I want to ask the class, what do you think about this? What will happen? Because it's objective, you have A, B, C, D choices, right? So please do that, please try and see if you understand, and if you understand, you can select which one will happen, and I want to see your answer in class, inshallah, right? So now we go to the group problem solving, another problem. Alright, so basically it is something like that, and then it's something like that. Okay, so basically it touches there, and then you have something like that, right? So my drawing is not that accurate, but it's basically like that, right? So you have point A here, point B here, point C here, and then you have the force there. That's it, 300 Newton, and then the angle is given as 30 degrees, right? And the angle here is also being given as 30 degrees. So if you have to draw the free body diagram, so the first step is again draw the outline of the shape of this. So it's something like this, right? And then you draw the forces, right? The dimension, of course. Okay, just a reminder, I do not show all the dimensions because I assume it's straightforward for you, right? You can draw it. I'm just focusing on the support direction and the forces direction. Right? So you have here 300 Newton at 30 degrees there. What will be the force here at point C? What do you think? Right? So it should be upwards, right? Because that's the perpendicular on the contact of the two objects, right? The two body, right? So this is perpendicular like this. What about point B? It should go also like that because that's perpendicular at the touching point there, right? What about point A? It should be something like this, right? Which is perpendicular to this surface there, right? So you should be able to draw the angle also, right? Because the angle is needed in your drawing, right? So when you draw the free body diagram, what will happen? It will happen something like that, right? And you have to label everything, right? The answer is exactly like this, with all the label of the dimension and the forces, right? Alright, so that's the free body diagram again. Now we have another group problem solving again for the free body diagram. So I'll just redraw it. Okay, again for this problem, you have the link of CD that we haven't learned yet. So it's quite interesting in the sense that we have learned to draw the free body diagram of something that we haven't learned yet, right? So let me check, because that one should be covered in 5.3 until 4.4. Where we deal with two force member basically, right? So should we cover two force member now, or because it doesn't make sense? You already learn how to draw it without understanding the concept of it, right? So I'll just touch on two force member, even though it's in the next slide. So I'll just include it here because Otherwise, you don't know why is that happening, right? So, this relates to the concept of equilibrium. In equilibrium, you have two things that you have to satisfy, right? One is summation of all forces equal to 0, and then summation of all moment equal to 0, right? Or in scalar term, if you are still covering 2D, summation of fx equal to 0, summation of fy equal to 0, and summation of moment equal to 0, right? You have three equations. Now, if you have a member like this, right, and you have all the forces acting on this member is only at this point and this point. Meaning that, for example, if you have force here, force here, force here, force here, force here, force here, whatever, but everything actually fall, all the forces actually fall only on two different points on the specimen, or not specimen, on the member, right? For example, like this. If you have force here in the middle, then it's actually all the forces acting on three different points, right? But now it's two, right? So this is, by definition, a two force member, right? Two force member, where the forces acting only at 2 points, right? Now, if this is to be satisfied, right? How? Right? So, of course, all of these force can be combined into one resultant force, right? For example, resultant force here, resultant force here, right? Now, for summation of force equal to 0, these two force should be opposite and the same value, right? Correct? This must be opposite and the same value, right? So either up and down, so it's opposite, or down and up, that's opposite. It will cancel each other, hence summation of force equal to 0. However, it also has to satisfy moment equal to 0, right? Let me give you another example. If you have something like this, right? Now, if I have some force like this, right? If it's exactly perpendicular, parallel and opposite with the same value, magnitude, force equal to 0, but moment will not, right? And this actually becomes a couple. We have learned when you have a force the same magnitude, parallel but opposite direction, that become a couple, and that actually contribute to this rotation for this case, right? But if it is in equilibrium, we need moment equal to 0, right? As well as force equal to 0. Now, without getting too long on this, the only way, right? The only way that this two is satisfied is when the force is actually making one line, either like that, and or like that. And as long as it goes through one line, then moment equal to 0, right? Because it's just one line, it doesn't have any distance. If you have a force like this, right, it have a distance, it have a moment. When it's just meeting like that, it doesn't have a moment, right? So that's the idea. So similarly here, to be force equal to 0 and moment equal to 0, it must create one line, the forces, right? And it doesn't matter what is the shape of the member. For example, if the member is something like this, right? And forces only act at those 2 points. Right? Okay, it's already outside of the. Okay, I'll just shorten this a bit. It's going out of the screen, right? Right? So, for this to satisfy both of these, the force should be along this line, right? Either in tension or compression. For example, this one is in tension, right? And the opposite is in compression, right? So when this is like this and the same value, then only then will this be equal to 0. Right. Now, why is this important? Right. So going back to here, right? Okay, I'll draw the question. Right. Going back to the slide of 5.1 and 5.2. So we have this member over here, and then this is a collar here, right? There's a collar. You know what's a collar, right? You know, there's a collar. No, I mean the collar, right? This collar, right? You understand? So when we talk about the collar, so it's basically just like something with a hole, and then it's basically like that, right? So it's just like the collar, right? Where your neck cannot move in this direction. You know, you cannot move that direction. It cannot move in this direction also, right? It cannot move in the direction also, your neck, right? But you can rotate. But you can only rotate in this direction, right? You can rotate here. But you cannot rotate this way, right? Meaning if the collar is fixed like this, you cannot rotate this way, you cannot rotate this way, but you can only rotate this way, right? So that's the collar, right? So you can only rotate this way, right? But you cannot rotate this way. You cannot, right? And you cannot also rotate this way, right? So it can only rotate about that axis, right? For example, right? That's a collar. But the way I explain it is actually 3D understanding. But it can slide, right? So for example, the collar itself, you can slide, but you cannot move in this direction, right? And you cannot move also in this direction, right? Like this one, this neck, if I have a long neck, I can move upwards, downward, but I cannot move this way, I cannot move this way, right? So that's a collar. And then you have a rocker here, right? A rocker there, and then this one is connected to another member like this, and then this one is pin, and then you have a moment here. This one is couple moment given by the question, 4 kN. And then you have a force here, 2.5 kN. And you have the angle, of course, 60 degrees. And then this one is 45 degrees. It's point A, B, C, D. Right. So this is the diagram, right? And okay, make sure you understand where is the member and where it is connected to a different member. For example, this way, right? Hopefully you can see how it's drawn. Now this is one member, one L member, right? Because this one is just at the end of the L there, you have a pin with a rocker. And of course, the rocker is not floating, it's on the ground like this, right? But this one, the member end there, and then this pin connected to a different member altogether, right? So what I'm saying is that you cannot cut off here. Suddenly you have one member like this, one member like that. You cannot, because that actually you cut off a certain member, right? So the member L should be still, when you draw the free body diagram, it will be that L. That L should exist like that, right? This L. And this is a different member, right? Can you see? Okay. So when you take out, this is one member, this is one member, right? Now we discuss this one first, because this is what we just discussed right now. If you notice, can you notice that this is two force member? Remember the definition? Two force member is a member where forces acting only at 2 points. In this case, is this 2 force member? How many points do you detect that force acting on this? There's one here with whatever color here, right? There's one here from this force. There's one here from this rocker and also the moment, and at the point here also, right? So yeah, 1, 2, 3, 4. So basically this is a 4 force member, right? So nothing special about it. But in this case, as you can see, the force is only acting on here and here. Hence, it becomes 2 force member. And if you understand what we just discussed just now, 2 force member, for it to be in equilibrium, because everything should be in equilibrium, so this should be in equilibrium. 2, the force need to be along that line, between the 2 points, right? In that case, it should be along the line that connected these two, right? So you can assume it's the tension or compression. Let's say I assume it under tension, meaning that the force is going out. The force is going out. Let's say if I write FCD, right? If I assume like that, meaning that here the force, the corresponding force should be FCD, right? Because this point and this point is actually point C. It's the same point, but when you detach, so you have to have this component opposite to each other, so that when you combine this and this to merge, it cancels each other, right? So that's the idea, right? So if you assume this one tension going up, then this one will be correspondingly like this, because it corresponding to this one. Okay. If you assume it to be compression going inside, this will be the opposite direction, corresponding to that one also, right? So that's two force member, right? Now, originally this one pin, right, and this one is pin, right? So if you draw actually these two at pin here, we have learned how to draw the figure, the separation of a pin. You have x component, y component, right? Similarly here, you have x component, y component, right? So originally it's like that. However, because this is a 2 force member, we know for sure that the force should be along this line. Otherwise, moment will not be 0, right? As you can see here, right? It creates a moment. So this must be equal to 0, this must be equal to 0 for it to satisfy, oh I have erased already, satisfy moment equal to 0. Right? Force equal to 0 is just as long as this equal, opposite, settle, right? So that's why it becomes like this. Because for sure, this is 0, this is 0. Otherwise, if it's have a value, then you will have a moment. You cannot cancel that moment, right? So that's why it becomes like this. Now, if this is not 2 force member, if it's not 2 force member, for example, there's a force here, or there's a monkey there that hang there, right? Whatever, which means there's a force there, means this is 1, 2, 3, become 3 force member, then it's no longer 2 force member, hence you have to draw like this. For example, if you have the force from the monkey, then this is not 0, this is not 0, right? Why? Because it is possible to have value to get the moment equal to 0, right? But if there's no monkey here, this must be 0, because whatever value here, the moment cannot be cancelled by anything here to get summation moment equal to 0. It has to be only like this, right? So make sure you understand why 2 force member is special, right? And you have to be able to identify, right? No one in the question in the exam will say this is 2 force member. No, you just look at it, the original question, right? Just by looking at it, I can see that okay, this member have only force at 2 points, so it's 2 force member, and hence it becomes like this, right? So we have discussed it here, right? What about here? Of course, whatever moment that you have given, you just draw, just like this force, right? Originally you got already, so you just draw. What about this rocker? Again, this rocker, the prevention is upwards, right? Because you can move to the right and to the left. You can actually move to upwards also, but you cannot move downwards because of the ground. So you have this reaction here, right? Normal reaction B, for example. Sometimes we use N for normal force, right? So this is NB because normal force at B. Right? If you draw downwards, it doesn't make sense because the ground never pull it down, right? It just push it up from something to go into the ground, right? Hopefully you can understand this. Why is there no movement? Because this doesn't prevent any rotation, right? The rocker will just rock. What about this one? As we mentioned just now, earlier, it's a collar, right? So the question is, can it move in this direction? It can, right? Because it can just slide along this axis. But it restricts movement perpendicular to this axis, right? Hence, you will have a force like that. Right? And E, for example, for normal force at E. Right? So that's the restriction. It cannot move in this axis, but it's free to move that way, right? So free that way, there's no force reaction. It is restricted that way, there's a force reaction. This is a pin there, so it is free to rotate. So you do not have any moment. Right? Now, okay, before I forgot, because there is a collar, right? If you have a collar like this, where it's a pin connected to a member there, right? For example. So when there's a pin, it allows that rotation, right? But if you have something like right, a collar like that, meaning that it's still free to move in this direction, it still restricts in this direction, but additionally, this one also prevent any rotation, right? You cannot rotate because this one is pin, right? Meaning the rod is at the pin, so it can rotate. But this one is like fixed, so it cannot rotate. So when you draw like this, when you draw the free body diagram of this one, so you have a restriction there, and you also have a restriction in terms of moment, right? So that is different than this one, where you only have one force there. You do not have any restriction of moment, right? So hopefully you understand how to determine what is support action there that you need to draw in the free body diagram, right? So in the end, you have something like this for this particular question, right? And one way to check if you actually have to calculate in your exam is the number of unknown should be less than the number of equation that you have. And in 2D, basically you have summation of fx equal to 0, summation of fy equal to 0, and summation of moment equal to 0. You have 3 equations. Hence you only have 3 unknown maximum, right? So in this case you have 1 unknown here, 2 unknown here, 3 unknown here. So you are good to go, right? If you do not know about 2 force angle, you might draw this y component here. Why? Because this is a pin. Normally pin will have x and y component, right? But if you do this, when you want to calculate, you will see that 1, 2, 3, 4. So you might miss something because in the exam, if you need to calculate, then the number of unknowns should be equal to or less than the number of equations, right? So if you have 4 unknown, something is wrong because you have to have mostly 3 for 2D problem, right? For 3D, then it becomes more. We will discuss that in the next recording, right? But now it's still in 2D. Alright, so hopefully you understand what we have discussed. And yeah, just a reminder before I forgot. This direction here, NA, this is a question for you, right? Can I draw it in the opposite way? Because right now I draw NA in that direction, right? Can I draw it in the red direction there? going down. Can I should, right? I can, right? Because this direction or this direction is just an assumption, right? Because it restricts this column here, right? It restricts movement here, right? Either that way or that way, both way it restricts. So you have to assume one way or another the support action. What about this one? Can I draw it downwards? What's your answer? No, you cannot, right? Because this will be wrong. Because what does it mean? Because this ground here can only support upwards. It just push upward. It cannot pull anything down, right? So this one will be wrong. This one, FCD, can I draw it to the left? Sure you can. Sure you can, because this one is assuming like this. The red one is assuming the opposite way, right? So you just have to assume when you calculate, you know, oh, it's positive, or it's negative. If it's negative, then oh, it's the opposite way of your assumption. That's all, no problem. Alright, so that's the end of 4.1 and 4.2. In 4.3 and 4.4, we will deal with how to calculate using the equation of equilibrium until we get the solution, right? And we will go back into the two force member yet again for the calculation, just to refresh, because in the slide is in this portion, but I just bring it up front because you have to understand why the slide suddenly have only one component here, right? Even though it's spin, because it's two force member. I'm not sure why the arrangement is like that, but yeah, okay. So yep, that's the end for this recording, inshallah. Hopefully you have understood, and this is very important because when you want to solve the equation problem, the first step is always free body diagram, and you have to, if you skip this free body diagram, one is you will skip the mark, right? You will not get any mark because they will be marked specifically for free body diagram in the exam, right? Secondly, we cannot even know your equation is correct or not, right? Because when you do summation of fx, summation of fy, or summation of moment, we should know that the force is positive or negative in terms of the direction. But if you do not draw, because for example like this, right? It can go both ways. Without the drawing, we cannot know which direction you assume. Hence, we cannot know whether your equation is correct or not, right? So that's why it's important, right? Similarly here, right? So without free body diagram, actually your equation doesn't carry any meaning, right? We do not know what is the meaning of that, whether it's a mistake, whether it's correct, etc., right? So that's why you have to have the free body diagram. Alright, so yeah, it's already 2:20 AM. So I need to sleep anyway. I have to go back and sleep. And what else? So I think that's it for this recording. Alhamdulillah. Hopefully you understand all of this, and do practice, right? I'm not sure if I missed out any of the support action, the different support action, but the idea is already covered, right? If it's preventing any motion, then you have the force. If it's preventing any rotation, you have the moment, right? So that's the idea. What else? Do some practice. Any question, you can ask in the comment or bring in the class, inshallah. Any which way is good. What else? So we end the session here, inshallah. Subhanakallahumma bihamdik, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. Wassalamu alaikum warahmatullahi wabarakatuh.